Hello everybody, my name is Thorsten Ball. I'm a software developer from Germany. I program in Ruby, in Go, in C, sometimes in Lisp. On the left, that's my name on GitHub. On the right, that's my name on Twitter, Thorsten Ball. I work for a company called Flink in Germany as a Rails developer, and we do dynamic ride sharing as a web application. The name of this talk is Unicorn Unix Magic Tricks, which is quite a mouthful and actually a weird title, so allow me to explain the title. Unicorn is a web server written in Ruby for Rack and Rails applications. And when I first met Unicorn, it seemed like magic to me. Unicorn had all these crazy features like this master worker architecture where you had one master process and 16 worker processes. Unicorn had this crazy master worker architecture, right? And it seemed like magic to me. And on top of this, it had hot reloading. As I said, hot reloading allows Unicorn to reload a new version of your application while the old one is still running. You can still serve old requests while the new version boots up. And this seemed like magic to me. And then Unicorn had all these crazy signals. You could send signals to Unicorn like the TTYN signal to increase the number of workers, or you could send the user2 signal to do hot reloading, the hub signal to reload the configuration, and the quit signal to do graceful shutdown. And Unicorn even had preloading, which somehow meant that Unicorn was able to preload my application, my Rails application, which, let's be honest here, takes around 10 seconds to load. Unicorn could preload this application in memory and then spawn off new worker processes in, let's say, 50 milliseconds. So all of this seemed like magic to me. But as it turns out, as I read through the Unicorn source code, it's all just Unix. It's all just Unix, down to the bottom. And now, most of you know Unix from the user's perspective. You use the shell, you use the command line, and so on. You use pipes, redirection, dot files. But there's this whole other side of Unix, let's say the developer's side, from which you can use Unix to your advantage in your programs and leverage the powers of the Unix system. And in this talk, we're going to look at how Unicorn uses Unix to build these great features it has. We're going to look at some basic Unix tricks, some basic Unix principles, and we're going to see how they work, how we can use them, and how Unicorn uses them. And the first Unix trick I want to talk about is fork. Fork is how every process on your Unix system gets created. Every process besides the first one gets created by a call to fork. So what is fork? Fork is a system call. That's what the 2 behind the name means. You can find the documentation for fork in section 2 of the Unix manual. Now, system calls are the API of your kernel. If you want to talk to the kernel, you have to issue a system call. And fork is just one of them. And what fork does is, as soon as you call it, the kernel splits your process into 2. You now have a parent process and a child process. And the child process is a nearly exact copy of the parent process. The children inherit a lot from the parent process. They inherit the data, the stack, the heap, the environment, the user ID, the current working directory, and so on. So how can we use fork? In Ruby, it's pretty easy. We just call fork. Now, in this example, we're calling fork at the top here and pass it a block. And in this block, we execute a bunch of code. This block is going to get executed in a new child process. So after this call to fork, we now have 2 processes. We have a parent process and a child process. The parent process has to wait because, and these are technical terms, in Unix system, the parent has to wait for its child to die or otherwise it turns into a zombie. Technical terms. So the parent has to wait for the child to die and then it prints something. Now if you run this, we can see that the output of the child process matches the process ID of the parent process. The parent process ID of the child process is the one of the parent process. And with just this call to fork, we created 2 processes, a parent process and a child process. If you use a tool like PS or PS3, we can see that it kind of resembles what we saw earlier with the Unicorn process architecture. So how does Unicorn use fork? Basically in the same way. This is a method, a small excerpt from a method called spawn missing workers. And all this method basically does is it runs a loop, and in this loop it calls fork a bunch of times. Now, the parent process takes the return child process ID because fork only returns in the parent process. It takes the child process ID and saves it. But in the child process, it's going into the worker loop. And after this call, after this method, we now have 16 worker processes going into a worker loop and doing something while the master process is free to do something else. And it's just a call to fork. This is pretty simple stuff. If you know how this works, it's really easy to understand and to use. With just a call to fork, we can create new processes. So let's talk about another Unix trick, pipes. I guess the majority of you have used pipes before. You use the output of one command and use it as the input of another command. But we can use pipes outside of the shell with another system call, which is surprisingly called pipe. If we issue pipe, we get two file descriptors back. File descriptors are numbers. They point to a file entry table in the kernel, which the kernel maintains for you, and in the end points to files. Now, pipe returns two file descriptors, one read end and one write end, because in a pipe the data only flows into one direction. The cool thing about this is that since it's file descriptors, child processes inherit these file descriptors, which makes pipes really great for communication between different processes. So if we use this in Ruby, it looks like this. We call io.pipe at the top here, which somewhere down the line, outside of the Ruby virtual machine, is going to call the pipe system call. And we get a read end and a write end back. And then we call fork and close the end we don't need because we want to write a message and we don't want to read the message. So we close the read end and write a message to the write end and close the write end again. In the parent process, again, we have to wait for the child to exit, and we close the write end because we don't need it. And then we read the message from the child process. In theory, this should work. And now we communicated between two processes. And if you run this, we see that it actually does work. And all we did was call fork and use a pipe for communicating between two processes in our system. This, again, is pretty simple stuff on its own. It's just the pipe you use in the shell, but now in your own software, in your own program. And Unicorn uses pipes a lot. If you boot Unicorn up and tell Unicorn to use 16 worker processes, Unicorn is going to open a pipe for every connection between one worker process and the master process. So you're going to have 16 pipes. And the master is going to write messages to these pipes to communicate with the worker processes. The other usage of pipes is a self pipe, which we're going to get to later. And this self pipe is only used in the master process itself, which Unicorn uses to talk to itself. And the other cool usage of pipes is when you start Unicorn as a daemon process. A daemon process in a Unix system runs in the background, like a server, right? That means it's not attached to the terminal. But if you want to start a process and detach it from the terminal, you have to call fork 2 times, which creates a grandchild. And Unicorn uses a pipe to communicate with the grandchild if it started as a daemon process. The master process waits until the grandchild writes a message that says, I'm fully booted up, I'm ready to go. And if it receives this message, it exits. Only then it detaches from the terminal. So it uses pipes to synchronize the booting up of a daemon process. This is pretty cool. So the next basic Unix principle I want to talk about is sockets and select. Sockets are everything you need to know if you want to do networking in a Unix system, and select is a great way to work with sockets. So what are sockets? Sockets are basically representations of connections. If you want to open a connection, a network connection, you have to use a socket. Now there are a bunch of different sockets. There are TCP sockets, UDP sockets, SCTP sockets, Unix sockets, raw sockets, and a whole bunch more. And again, sockets are just files. You probably heard this. In Unix, everything is a file. Well, this is it. Pipes are files and sockets are files too. These are just file descriptors, which means that children inherit those sockets. But if we're a web server, a network server, we have to do more than just call the socket system call. We have to do something like this, which is the basic Unix networking socket lifecycle. We have to call socket to create a new socket. And we specify the family, if it's IPv6 or IPv4, if it's UDP or TCP, raw socket, and so on. And then we call bind to bind this socket to a network interface on a port. And then we call listen to turn this socket into a listening socket, which means it's a passive socket. It's a server socket. It's going to accept incoming connection. This tells the kernel, hey kernel, if there's an incoming connection on this port, please forward it to me. And after this, we're going to have to call accept. Accept is going to block until there is a new connection. Until you have a new connection available, accept is going to block. Which makes it kind of hard to deal with more than one socket, because if you're going to block with accept on one socket, how are you going to call accept on a different socket? And this is where select comes into play. Select is another system call which does multiplexing. It monitors file descriptors, which sockets are, or pipes are, and files are, and returns only if one of those file descriptors is readable, writable, or has an error. That means, since select is blocking, we can switch out accept for select. And by using select, we can do this. That's 23 lines of Ruby, and it's basically a fully functional multi-process TCP server. If you add like error handling, it's production ready, I'd say. Seriously, what we're doing here is we're creating two new sockets with socket.new, which somewhere down the line is going to call the socket system call. After this, we're binding those sockets to addresses, to network interfaces. And then we call listen with the backlog queue, which means the kernel is going to enqueue 10 connections and turns this socket into a passive socket, into a server socket. And after this, we're going to call fork 5 times to create 5 child processes. And in these child processes, we're going into our own worker loop. We're going to call io.select on these 2 sockets, which is going to block until one of those sockets is ready for reading, which means there's a new incoming connection. As soon as there is a new incoming connection, we accept this connection, read the message from it, close the connection again, and start the whole loop all over again. Now, if you run this on the left as our server and use a really sophisticated networking client constructed with Echo and Netcat and send 5 different messages to our server, we can see that our server received these messages in different child processes. What happens here is that we shift the control over to the kernel by using io.select, and the kernel is doing load balancing for us. The kernel chooses which child process receives the new connection, all by doing just a call to io.select and using fork and child processes, which all call io.select on the same sockets. And this is what Unicorn does too. When Unicorn boots up, it also creates a listening socket. It calls socket, bind, and listen. It creates a listening socket. And after this, it creates pipes for the workers to communicate with the workers, and then it forks. And now it has 16 worker processes. And the worker processes are going to call io.select on the listening socket and on the pipe connecting to the master. So the workers accept incoming connections on the socket, but they are not going to miss any messages sent from the master process because they're calling io.select with both those file descriptors, with the pipe and with the socket. And that's all there is to it. And this allows Unicorn to have more than one listening socket. You can tell Unicorn to listen on port 8000, 9000, 7000, and Unicorn doesn't have to change anything. There's no switch statement, no if statement in there. It's the same architecture. Unicorn just uses io.select and forks off a bunch of workers which are going to call io.select on the different sockets and on the pipes. That's pretty easy, again. So, another huge Unix topic, signals. Again, a lot of you have probably used this before. Kill-9, maybe with sweat running down your face. What this does is, it sends the kill signal, the signal with the number 9, to this process. Now, signals are software interrupts. By sending a signal to a process, you go into the kernel and you tell the kernel, hey, kernel, please deliver this signal for me. And the kernel is going to deliver this signal. And the process is going to jump to a signal action. It's going to handle this signal. And this is what we call signal handling. Now, for signal handling, we have different options. We can redefine signal actions, signal handlers. We can tell the kernel, if I receive the quit signal, I don't want to exit, which is the default action. I want to clean up some files and then do something else and then exit. Or we can ignore signals, or we can redefine the default actions or define our own signal actions. The only limitation is that we can't ignore or redefine the action for the kill signal because there has to be a sure way to kill a process on a Unix system. Again, using this in Ruby is easy. We just call trap to trap a signal. And we call trap and pass it a block. And this block is going to get executed as soon as we receive the message, the signal. If we're going to receive the user signal, it's going to print user 1 received. And at the end there, we're printing our own process ID so we can send signals to it, and then we're going to sleep for 100 seconds so we have time. Now, if we run this as our server on the left, and again, we use a highly sophisticated client on the right and send our signals to our server, we can see that our server executes those signal actions we just sent with the kill command. But again, the only limitation is we can't redefine the signal action of the kill signal. What Unicorn does is a bit more complex. Unicorn has a whole lot of different signal actions, as I said before. There's some crazy features behind those signals. You can reload the configuration file. You can increase or decrease the number of workers. You can shut down the workers and only have the master running. You can do hot reloading, and so on. Unicorn has a whole separate API just consisting of signals. But since signals are asynchronous events, they're software interrupts, you never know when they're going to happen, they're pretty tricky to deal with because let's say your signal action for the quit signal is deleting some files. And while you're deleting files, you receive the quit signal again. What is your signal action going to do? To work around this, Unicorn has its own mechanism for dealing with signals, and this is the self pipe I mentioned earlier. When Unicorn boots up, it creates a pipe and a queue. Queue is the data structure, a queue. Now, it sets up different signal actions. The signal handlers themselves, the actions, they do nothing. They only write the name of the signal they just received into a queue and write 1 byte to the self pipe. The master process, while it's running, has a main loop in which it checks up on workers, it checks up on network connections, and so on. And it sleeps in this main loop by calling io.select with the timeout on this pipe. Now the master wakes up as soon as there's 1 byte on this self pipe, which means there's a new incoming connection. And all the master process has to do is, as soon as it wakes up, it has to pop off 1 signal of this queue and then execute the signal action in its main loop. And this way, by using a pipe, Unicorn essentially turns the asynchronous events, the signals, into a synchronous stream of signal names it can act upon in its main loop. And again, that's just pipes and signal handling combined in a really clever way. Is all of this magic? Forking, sockets, select, signal handlers? No. It's pretty simple stuff, right? On its own, all of these building blocks are pretty easy to understand. So now we're going to take a look at those crazy Unicorn features I showed you in the beginning, and we're going to see how they work with these simple Unix tricks. The first one is preloading. As I said before, Unicorn allows us to preload our application in memory, which I guess you can probably imagine how this works by now. But it allows Unicorn to only boot the Rails application. Let's say it takes 10 seconds once, and then it can use the loaded Rails application in the worker processes. And it works like this. The master process boots up, and it defines a lambda. And this lambda is what loads your application into memory. In this lambda, it uses your config.ru file, it uses the rack builder, it constructs middlewares, it requires your Rails environment, and so on. It essentially loads your whole application into memory. But the lambda is only called if you tell Unicorn to preload the application. And if you do, the master is going to call the lambda, which loads your whole application into memory in the master process. And all Unicorn has to do now is call fork, because the child processes inherit the memory of the master process. They inherit the data, the stack, and the heap. They now have this Rails application in memory, and they don't have to wait 10 seconds anymore. This is really cool how Unicorn uses just the semantics of fork to accomplish this great feature. Another great feature is scaling workers with signals. You can send Unicorn the T2IEN signal, which increases the number of running worker processes. Or you can send the TTOU signal to decrease the number of running processes. And how this works, again, is pretty simple. The master process boots up, and it defines signal actions. And again, these signal actions do nothing more than write the name of the signal to the queue and write a byte to the self pipe. Now the master process wakes up because there's a new byte in the self pipe. And it sees that it received the T2IEN signal, which means increase the number of worker processes. And what it does then is it increases the variable worker processes. And after this, it's calling this method, which we saw earlier, the spawn missing workers method. But now it has to do one more iteration of this loop. It's going to call fork one more time. But that's it. That's all there is to it. It just increases one variable and runs this loop one more time, which creates a new worker process. Everything the worker process needs is already in memory. Now, as you can see, the master process remembers the number of the spawned worker process. So if you have 16 worker processes running, the last one has the number 16, which comes in quite handy if you want to decrease the number of running processes. If you send Unicorn the signal TTOU to decrease the number, it calls this method, maintain worker count. And all this method does is it checks if there's a difference between the number of running processes and the number of processes you requested it to run. If there is no difference, it returns. If there are not enough processes running, it calls spawn missing workers, which we just saw. But if there are too many processes running, it finds the one process, the one worker process with the number that is too high. If you want 15 worker processes, it's going to single out the one with the number 16, and it's going to call soft kill. Now, it's not sending a signal to this worker, no. Soft kill actually writes the name quit on the pipe, through the pipe to the worker process. The worker process is handling the connection, and when it finishes, it calls io.select again, and now it sees that the master process told it to quit, and then it shuts down. With this, Unicorn actually does graceful shutdown of worker processes. The workers are finishing their work before they're told to quit, all by using, again, a pipe and io.select. And again, this is pretty simple stuff. But now to my favorite feature of Unicorn, hot reloading. As I said, some people call it zero downtime deployments, rolling restart, hot swapping, and so on. Unicorn calls it hot reload, and it allows us to spawn off a new master process with the whole own set of worker processes with the new version of our application while the old one is still running. And as you can see, the parent process of the new master process is the old master process. So how does this work? So let's say the master and the worker process are happily doing their work. The master is in its main loop, it's going to sleep, it's checking up on workers, and so on. But the worker processes are handling connections. And now suddenly the user 2 signal arrives, which means Unicorn, please do a hot reload. And again, the signal action just writes the name of the signal to the queue and writes a byte to the self pipe. The master process wakes up from its main loop, from the sleep, and it sees that it has to do hot reloading. And it calls a method called reexec, which is this. As you can see in line 2, no, I'm just kidding, of course. I'm going to walk you through it. All reexec does is this. First of all, it does a sanity check. Am I already hot reloading? If so, then exit. Then return. Next, it writes its own process ID to the pitfile.old, so we can remember the old master process. And then it calls fork, which creates a new child process. This new child process is not going into the worker loop. What it does is it closes all the unneeded files it doesn't need. Database connections, log files, configuration files, and so on. It only keeps open the listening sockets, the one we told Unicorn to listen to. And it takes the file descriptor numbers of those sockets and writes them to an environment variable, which sounds nasty, but it's actually quite cool. So it writes those numbers to an environment variable and then calls exec. Exec is a family of system calls. Exec turns a process into another process. If you use your shell, the bash, and type in vim, what bash does is it calls fork, which creates a new bash process, and then it calls exec to turn this new bash process into a vim process. And this is what Unicorn does. It calls exec with the original arguments it was called with. That means it turns the new child process, which is not in the worker loop, into a new Unicorn master process. And the new Unicorn master process boots up. And what it does then is it checks the environment for those file descriptor numbers. And if there are any numbers in the environment, it takes those numbers and casts them into I/O objects. And it's able to do this because it inherited those sockets. It doesn't have to open new sockets. Those are the same sockets the old parent process opened. The new master process just casts them into I/O objects and can use them again. And then it calls fork a bunch of times, creates new worker processes, and they are going to call io.select on this socket again. And the whole time there is no address already in use error, which would happen if you start another master process without it being the child process. No, it's the same socket. And all Unicorn does is it uses fork and the semantics of its inheritance mechanism. Unicorn uses fork to take those sockets and pass it onto a new master process. In this way, as soon as the new master process boots up, it uses the same socket and handles requests with the new version of my application without any downtime at all. The old master process is still running, and we can take its process ID from the pid file.old and kill it. And after this, we only have the new master process with the new version of our application running, and that's it. That's zero downtime deployment in Unicorn. And as I said, all of this is no magic. It's simple stuff, really. If you know how fork works, how sockets work, how select works, it's pretty easy to build stuff like this. It's just a combination of these simple things, of these simple tricks that make these great features. And now you might ask yourself, why should I know about this stuff? I'm an application developer. I'm a Rails developer. Why should I care about sockets? Why should I care about system calls, select, Unicorn, and Unix? I think there are great reasons for caring about this stuff. And the first one is debugging. Your Rails application is probably going to run on a Unix system in production. And if you know how Unix systems work, you're probably going to know how your application is going to behave in production. If you have ever seen the error message, you cannot open a database connection after forking, or you cannot call fork after opening a database connection, now you know why. Because the child process is inheriting this database connection, and using it from two processes would lead to race conditions. Another reason is design and architecture. How are you going to make informed decisions about your system and how it's going to work if you don't know how the underlying system is working? How are you going to choose to use this process or this process if you don't know how these processes could communicate with each other? And the next reason is basically a quote. Somewhere someone said, it's always good to know one more level of abstraction beneath the one you're currently working on. And I believe in this. I believe that learning to program in C made me a better Ruby developer. And I believe that knowing about Unix and about Unicorn made me a better Rails developer. Because at the end of the day, I'll know more about my application and how it's behaving in production. But the last and most important reason for me personally is the satisfaction I got from finding out that all of this is not magic, that it's not written by some wizards far away in the basement, but that it's just simple stuff, and maybe I could build software like this by combining the same simple things in the same clever way. And with this, thank you very much for listening. And if you want to talk about this stuff, please come and find me. Talk to me. I love to talk about low-level programming, Unix, and Ruby. Thank you. Are there any questions? How to what?
Hot reloading.
Hot reloading, yeah.
So you said that the time process works, and they execute another multiple.
Yeah.
And then the old part is still lying inside, doesn't make.
The question was, if you do hot reloading and the old master process is forking and creating a new master process by calling exec, and the new master process is calling kill on the parent process, if this doesn't leave the new child process as a zombie, right? Yeah. Normally, you don't kill your own parent. No, I mean, seriously, I don't know actually what would happen if you do this, but most people just use like upstart or something to kill the old process as soon as the new one is booted up. And you can, Unicorn has hooks in which you can define what to do as soon as it's booted up. And if it writes the old PID file there, you know that it's fully booted up and you can kill the old process. Any other questions? Yes?
Just answering the question, I think it's not a zombie because the parent can also detach from child. So the system knows that it's not waiting on them and they're not zombies. So that's one thing. I think that might be happening. Another thing is that I think in new kernels it's possible for processes to start using the same socket without like inhibiting the parent.
Yes.
And do you think it makes sense to have like universe workers without the parent?
Yes. So the first part was, yes, you can kill your own parent, all right? It doesn't leave zombie processes. And the second part was, if it's possible, or it is possible, to use the same socket from different processes, which don't share the same parent process. And yes, this is possible. I think it's in Linux now. It has been in FreeBSD for a longer time. That means you can start different processes and they have not the same, one is not the child of the other. They're different processes and they can use the same socket. But that you have to change the socket system call to tell the kernel that you're doing this, and then it's possible. But it's still a pretty new feature. It landed in Linux, I think, a year ago, or 1.5, and it has been in FreeBSD for a couple of years longer.
In fact, you can pass a file descriptor using a unique socket, and that's
yes, exactly.
That's it.
Yeah. You can also do IPC in Unix, and you can send sockets file descriptors to other processes. You can send Unix messages. You have to pack them in a different way, and you can send file descriptors to other processes. Yes. All right.
Okay, so
thank you again very much.